So, hi everyone, my name is Annika, and this is my project submission for the second idea of OASIS Python Development Internship for April 2026. The project is called BMI Pro, a precision wellness tracker, and it's a full stack application built with Python on the backend and a custom HTML interface on the front end. The tech stack includes, as you can see, Python 3, NumPy, and SciPy for all scientific calculations, and Flask REST API connecting the two layers, and a fully custom animated HTML and CSS interface. Let's get into what I built and why. First, the task actually. So the task had two levels, a beginner version and an advanced version. For the beginner task, I had to build a simple command line BMI calculator in Python, taking the user's weight and height, apply the BMI formulae, classify the results into categories like underweight, normal, overweight, or obese, and print the output. Now, for the advanced task, the bar was raised significantly. I had to build a full graphical interface with a nice UI, implement data storage for multiple users, allow historical BMI viewing, and do proper trend analysis with statistics and graphs. So, yeah, basically, I went above and beyond on both, as you will see. I implemented all 7 advanced requirements, fully including 3 body fat formulae, 4 ideal weight formulae, 3 BMR equations, TDEE with 6 calorie targets, waist to height ratio, and statistical trend analysis using SciPy linear regression. Everything you see here, by the way, is working, tested, and running live. So, actually, before I show the live demo, let me quickly walk you through the science powering this app. First, BMI. It is the World Health Organization standard, weights in kilograms divided by height in meters squared. I implemented 9 WHO classification tiers from severely underweight all the way to obese class 3. For body weight percentage, I didn't use just one formula, I used three. First, the Deurenberg from 1991, Jackson-Pollock from 1978, and the CUN-BAE from the University of Navarra. The app takes the mean of all three and reports a 95% confidence interval, so the estimate is statistically robust rather than dependent on a single equation. Then comes this ideal weight, the ideal body weight. I implanted 4 clinical formulae: Devine, Robinson, Miller, and Hamwi, each originally designed for different medical contexts, though again the app gives you the ensemble average. BMR or basal metabolic rate is calculated 3 ways: Mifflin-Senghor, which is the gold standard, Harris-Benedict using the Rosa 1984 revision, and Katch-McArdle, which actually uses lean body mass rather than total weight, making it the most precise if your body weight percentage is known. Then comes TDEE. Total daily energy expenditure is your BMR multiplied by an activity factor ranging from 1.2 for sedentary to 1.9 for athletes. This gives you 6 personalized calorie targets. Then finally we have the WTHR, a cardiometabolic risk indicator that research shows is actually better predictor for heart disease risk than BMI alone. Below 0.5 is healthy, 0.5 to 0.6 is overweight risk, above 0.6 is high risk. And for the trend page, all statistical analysis runs through SciPy's linear regression, as you're going to see, giving us the slope, R-squared, p-value, moving average, z-score, everything, and a predicted next level BMI value as well. So now let's actually see it all in action. But before, let me just quickly show you the project structure. It's intentionally clean, just 3 files right here. Run.py is the heart of entire application. It contains the Flask server, all the API routes, complete calculation engine, HTML interface, all embedded in one file. When you run it, it installs its own dependencies and opens the browser automatically. And it also contains the engine section inside this. So where all the scientific computing happens using NumPy and SciPy. We'll see to it. And we have the README. So you get the whole structure and the requirements for a quick access to all the dependencies that you would require to run this. Now, let's look at the engine now. So first off, there's this calc BMI function. This is the BMI category function. It checks age and applies different threshold for under 18s versus adults, giving us 9 classification tiers for adults. Then comes the body fat, this one. So there are 3 functions here. These 3 functions, so the BF Deurenberg, BF Jackson-Pollock, and the BF CUN-BAE, right, are the 3 body fat formulae. Notice each one takes BMI age, okay? So here they are taking the BMI age and the sex. The body fat ensemble function below runs all the 3, puts them in a NumPy array and calculates the mean standard deviation and a 95% of confidence interval using 1.96 sigma rule. Then comes the IBW functions. Again, the same pattern here for ideal body weight. 4 separate functions for Devine, Robinson, Miller, and the final is the Hamwi, and an ensemble function that averages them using numpy.mean and numpy.std. Okay. Then we have the 3 BMR functions right here. So these functions follow established clinical equations. As I said, the catch McArdle is one interesting one. It first calculates the lean body mass and weight and the body fat percentage, then uses that in formula, making it more accurate than height weight only equations. Then comes the analysis trends right here, this one. So this function, so this is where SciPy comes in. Stats dot line regress here gives us everything: the slope, intercept, r squared, p-value, standard error in one call. I also compute a moving average using numpy dot convolve a z-score for latest entry and project the next BMI using the regression line. Then we have the Flask clear right here. Flask clear is straightforward. The route serves the HTML interface directly from memory, not from a file, which is why it works on any machine without path issues. And this API calculate, this post method, the route receives JSON calls, full analysis, and returns the complete result object. There are also routes for saving entries, retrieving history, deleting individual entries, clearing all data, and fetching trend data. All histories stored in a local JSON file in the data folder that it always makes when it's running. So let's actually see the live application now. Okay, so here's the live application running locally on port 5050. The UI is built entirely with HTML, CSS, and vanilla JavaScript. There are animated background blobs, as you can see them floating. Floating particles, these glass morphism cards, all CSS animations, no external UI frameworks have been used. Now you can see the top here. The ribbon suggests you for a calculator, history and trends, starting with the calculator first. Let me just type my name. Okay. My age, say it's 20. Female, height 1 cm. Okay. and I'll just type it as 65. Oh, sorry. Okay. Circumference. So the gender selection affects the body fat formulae, as I mentioned, and the BMR equations. And the unit matrix, by the way, are also here in kilograms. You can also just switch it from this UK system to this US system if you want. Also, this waist one, this waist circumference, this is optional but enables the waist to height ratio calculations. And then you have the activity level. Moderate is just fine, I think. And we can just analyze it right now. And it gives the scores real time to you as you keep moving your values around. So the request goes to the Python backend. It runs through all the formulae and returns the full result, which we can see in this animated gauge, as you might have seen. Below that, we have the estimate of the body fat percentage using ensemble mean and lean mass in kilograms. Now, this body fat analysis, if I expand the body fat accordion, I can see all the three individual formulae, the Deurenberg, Jackson-Pollock, and the CUN-BAE, the ensemble mean with standard deviation and 95% confidence interval. This level of detail is what separates this from basic BMI calculator. Then we have this ideal body weight accordion, 4 formulae again, all slightly different with the mean shown at the bottom. For this height and gender, the ideal weight range is about 57 to 59, which is, it will just suggest to you. Then we have the BMR and TDEE. Three BMR values, the average BMR, TDEE for moderate activity, and 6 calorie targets. If I want to lose half a kilo per week, I'd eat around 1800 calories, something like that. And then we have a health tip over here. And this one is a personalized health tip, by the way, based on the categories. And I can save it as an entry. It gets written to the JSON history file on disk. Now let's switch to the history tab right here. You can see the saved entries. These were some of them priorly. You get the name, timestamp, height, weight, BMI, and the category badge. The history is persistent. It survives between sessions. Each entry is clickable, right? It reloads to those inputs and there's a delete button per entry, and to clear all of this, so say if I want to delete this one, I can just do that, or you can just clear all. We have already a second entry, so we can just move directly to the trend. You at least need two entries to get a trend. So with two or more entries, the SciPy regression kicks in. Here's the chart.js line graph showing BMI over the solid line. The solid line here is actually the values, so you can see it slightly declining here. The dashed line is the moving average, and the lighter dashed line is the linear regression trend. And below the chart, you see the mean BMI, the lowest records, and the highest change between last two entries. And the stats table right here. Here's the full SciPy output, the slope of the regression line R squared, which tells us how well the line fits the data, p-value, standard deviation, median, z-score of the latest entry relative to the history, and the predicted next BMI if the trend continues. So this is what proper data analysis looks like, not just plotting points, but running actual statistical inferences. So here's the full thing. BMI Pro is a full proof Backend plus front-end full-stack wellness application with a Python precision engine running NumPy and SciPy on the background. A Flask REST API serving 7 endpoints and a fully custom animated HTML interface, as you can see, for the front end. It implements the complete OASIS advanced task multi-formula body fat analysis, 4 ideal body weight formulae, 3 BMR equation, TDEE, and calorie targeting, persistent multi-user history, SciPy trend analysis, and ways to height cardio metabolic risk. I thank you for watching.